Well, welcome to the second lecture. Like I said, there will be another lecture tomorrow at 10, same place here. And we'll meet again here at 4 for further sessions. It's open and it's informal. We want to discuss and try to digest what's been said during the lectures. That's the idea. So there won't be any further structure of the lectures, more than that. And the announcement is that if you guys want to have lunch all together, we can go to a place which is not very far from here, and Jornadas can pay for it. So if we can, well, Leticia's project is basically paying for this, and we can leave from the institute, say 1:45, 1:50, and it will take us 10 minutes to walk there. And it's good food, and it's many of you probably you already know this place. It's Comala. It's good food, and the place is pleasant. All right, so everybody's welcome to join for lunch. To join us for lunch. Okay.
All right. So maybe what I'll do today is tell you a little bit about Bridgeland stability and how to use that to sort of compute cohomology sometimes. Okay. So X will be again a smooth projective surface, but you can talk about Bridgeland stability more generally. So maybe let's do that a little bit. So X will be a smooth projective variety over the complex numbers. And then you see you have the bounded derived category of coherent sheaves on X. So which we will denote like this. This is the bounded derived category of coherent sheaves. And you shouldn't be afraid of these things. I mean, there's a lot of scary sounding things, but at the end of the day, it will boil down to like solving some quadratic equations. So it's, the point is that this is a triangulated category. It's not quite an abelian category. So, you have these exact triangles. And so then here is the definition. This is what the Bridgeland stability condition is. So let's, a Bridgeland stability condition on this bounded derived category is two pieces of data. So I have a category and a function, okay? Is a pair like this, such that let me now tell you what these things are and what axioms they need to satisfy, okay? Is a pair like this, such that first, this thing is an abelian subcategory of this bounded derived category, and what's called is the heart of a bounded T structure, whatever that means. We don't care too much. So A is, the heart of a bounded T structure, the heart of a bounded T structure. And the way you should think about this is that this is just an abelian subcategory of your derived category, and it's not a dumb one. It's sort of sensible enough that shifts in certain extensions generate the bounded derived category. Okay, so the way you should think about it, this is a sensible abelian subcategory. Sensible abelian subcategory. And if you want to read more about these kinds of things, I think there's this book on homological algebra, I think by Manin, that you can read these kinds of exact definitions for these kinds of things. And so this is some abelian subcategory, and this is some function. So this is a group homomorphism from the K group of the bounded derived category to the complex numbers. This is a group homomorphism. So I told you what the pair is. You have an abelian subcategory, which is the heart of a bounded T structure, and you have a group homomorphism from the K group to C. And now we need some axioms to be satisfied, satisfying the following axioms.
The group in the group is the same as the group of
That's right. So K of this is the same as K of A. Or if you want, even K of coherent sheaves. Okay? Minus
what is K?
Sure. I mean, so like, you know, the K group is, you know, let's do it for sheaves if you want. So you take the, you know, the free abelian group on your sheaves, modulo if you have, you know, an exact sequence, E goes to F goes to G goes to 0, then, you know, the class of F is the same as the class of E plus G. Okay, modulo those relations. I said that fast, but the K group is you take the free abelian group on your sheaves, and each time there is an exact sequence, you declare that you make the relation that the middle one is the sum of the outer two. Okay? All right, so now they need to satisfy some things. So the first thing is the first condition. So the first condition is positivity. And what that says is that if you have a non-zero object of your heart, then this goes to the upper half plane. So if you have some E in your heart, which is not 0, I mean, of course, 0 has to go to 0 because this is the group homomorphism, then this Z of E is in the upper half plane, and the upper half plane includes the negative reals, but not the positive reals. Okay, so this is the set of things of the form rho ei theta such that rho is positive and theta is between 0 and pi. And pi is included and 0 is not. Okay? So the image of every non-zero object lies in the upper half plane. This turns out to be the hardest thing to ever satisfy. Like, this is hard. Okay? So this is positivity. The next condition is the Harder-Narasimhan filtrations. Harder-Narasimhan filtrations. Okay? And what that means is that every object should have a finite filtration. So every object. So let me make a remark. So once you know that Z of E is in here in the upper half plane like this, then you can define a slope. So you know, this allows us to define a slope. That under this condition, the function Z defines a slope. And how do you do it? Well, basically so the Z slope of this thing will be, you know, minus the real part of this Z divided by the imaginary part of this Z. So if I want to talk about a slope, right, then, you know, I put in my object in here, then you look at real part of Z divided by the imaginary part of Z. And now you see the tricky part is that what happens if this imaginary part of Z is 0, right? And then that's precisely, we rigged it so that it becomes well defined. And then, you know, when you are here, then you get infinity, and otherwise it's not, you know, it's a finite number. Okay? So because that we have the slope function, now we can start talking about semi-stability. And again, what does it mean to be semi-stable? Just like when we defined it with regards to the Mumford slope or the Giesecker slope or anything like that, you call an object semi-stable if no sub-object has bigger slope. Right? So let me maybe write that. So this allows us to define, you know, we can start talking about semi-stable objects. So we can talk about semi-stable objects. And that means that, you know, if you have an object E in A, then this is mu Z semi-stable if for all sub-objects, I don't know, E prime of E, right, you have that mu Z of E prime is less than or equal to mu Z of E. And then, you know, you can make it stable by not allowing, sorry, this is, let me write it over here. mu z of e prime is less than or equal to mu z of e. So you see, I can start, the moment I have such a function, I can start talking about, stability, and you see, things will work well because if you have exact sequences, because this is a group homomorphism, then it will behave the right way. Okay, and then the next thing that you want to have is that every object should have a finite Harder-Nursemhand filtration. So every object has a filtration. Every object of A has a filtration of the form that you have E naught maps to E1 maps to En. This is equal to your E. This is my object that I'm trying to filter. This I take to be 0. And you see, this is a triangulated category. So, you know, I don't have quite exact sequences, but I have triangles, right? And so the requirement is that these AIs should be semi-stable and decreasing slope. So the AI, so the AI are mu z semi-stable with mu z slope of A1 bigger than the mu z slope of A2, and so on and so forth. And then finally, there's one more thing that you require, and this thing is called the support property. I'm not going to belabor that point much. So I'll just say that, just make you aware that there's one other axiom that I'm going to ignore. Okay? But so the main things are this. There's this positivity property and the Harder-Nursemhand property. And then you want this thing to vary well, so you put some other condition, but we are not going to. We are not going to do any fancy constructions here. We'll just stick to surfaces where, you know, things will be fairly explicit. And now you see the main theorem. So that's a Bridgeland stability condition. Let me maybe briefly repeat. So you have some abelian subcategory of your derived category and a homomorphism, a group homomorphism from the K group to C, such that it's positive and every object has a Harder-Nursemhand filtration. Okay? And then
You don't need here that the homomorphism from one to the other are 0?
you would get that automatically. You would get that automatically by this definition. Okay? I mean, it really acts like a stability. Okay? All right, and then the main theorem of Bridgeland is the following thing. You can look at all possible Bridgeland stability conditions on your X. Yeah? So call that stab X. Stab X. This is the set of Bridgeland stability conditions. Conditions on X. And then the theorem says the following thing. This stab X is a complex manifold. Unfortunately, possibly empty. Even though we think it's not empty, you know, we don't know that it's not empty. And then the point is that, in fact, if you look at the map from AZ to Z, so you just forget the abelian category and you just look at the function, then this is a local homeomorphism. So this is a local homeomorphism onto its image. Local homeomorphism onto its image. And, you know, of course, this Z, right, I mean, you know, is hum from this to C is just the complex vector space. So this is what induces the complex manifold structure. Okay.
And the possibility that is an algebraic variety?
No.
No?
I mean, no. I mean, it's, I mean, I mean, it depends on what you mean by algebraic variety, but
I mean, it's possible to embed it in some projected space.
I mean, they won't be projective.
No?
No,
Okay.
no. I mean, yeah. In fact, it's expected that they're contractible in most cases. I mean, it's more like a vector space. You should think of it as an open set in a vector space. Okay?
Yeah, I mean, I always wonder what kind of structure has.
Right. All right, so maybe let's see an example or two. So let's see an example and a non-example, okay? So let's look at an example. So let x be a curve. And now I can ask, so how do you want, what do you want to do? Of course, I mean, it's easy to do. A is coherent sheaves on x, right? I take A to be coherent sheaves on x. And what should z be? Well, I mean, you take the minus the degree plus I times the rank. Okay? And then what's the slope in this case? Well, I told you what the slope was. It's the real part over the imaginary part. So mu z is the degree over the rank. And so then this is nothing other than Mumford's slope. Okay? And then, you know, the Harder-Narasimhan filtration is the usual Harder-Narasimhan filtration. And then the positivity, you know, it works like this. So let's do the positivity. So I have the imaginary, what's that? I have the imaginary part, right? So if you have a coherent sheaf and it's not torsion, then the rank is positive, and so that's good, right? On the other hand, if it's torsion, then the rank is 0, but then the degree can't be 0 unless it's 0. So then the degree is positive, so that you see that you're in the negative real axis. Okay? That's the basic example for a curve. All right, so now let's do a non-example.
And in that case, stop.
It turns out that it's just like a PGL in that case, because you know there is something called what do you call that thing? I mean, yeah. I think the point is that GL2R plus acts on this thing, on this picture. Like basically you rotate this thing and then you rotate the function at the same time. And then basically, as long as the curve has genus at least 2, this is up to that action the only thing. It's the only stability condition on the curve if the genus is at least 2, I believe. Yeah, up to that action. So then, you know, this is some GL2R plus, the universal cover of GL2 or something like this. All right. Okay. So now let's do a non-example. Okay, so now we do X a surface. Project a surface, yeah. I mean, why do anything complicated if you don't need to do it? So let's do A is again coherent sheaves, right? And, you know, we are in good shape, so we also have the Mumford slope there, so do minus the degree with respect to some ample, you know. Or, you know, take the surface tab, pick our rank 1 or something like this, minus the degree plus I times the rank. Maybe this is with respect to some ample. Okay? Now the claim is that this is not a stability condition. Now what goes wrong? I mean, the Harder-Narasimhan filtration is still fine. I mean, you still have Harder-Narasimhan filtration. Of course, what always goes wrong is the positivity. That's the hard one to satisfy. So now let's think about this. Okay, if the rank is equal to 0, right? I mean, as long as the rank is positive, then you're in the upper half plane. But the problem is that if the rank is 0, then you know, you have some torsion sheaf, but the torsion sheaf can be supported along a curve, right? In which case this degree will be positive, which will be okay, but it could also be supported along points. So if you have a skyscraper sheaf supported at a point, right, then this is 0 even though the sheaf is not 0. So positivity fails here. Positivity.
And that happens for any variety, no?
This will happen for any variety of dimension bigger than 1, yes.
So the move for stability is not a Bridgeland.
No, it's not a Bridgeland that's other than curves.
And the problem are torsion sheaves.
Yeah,
For torsion supported in codimension 2 or more. For torsion sheaves. For torsion sheaves supported in codimension 2 or more. Okay? And in fact, just to make you even feel worse. So, in fact, there is no z which makes the coherent sheaves on X. Like there is no Bridgeland stability condition where the heart is the coherent sheaves on the surface. Also in higher dimensions, but just to make you, so one has to do something.
So you mean that if we restrict to the coherent category?
Yeah. It's not going to occur as, you need to do something with the T structure before you can construct these things.
Okay, the A is not a fiber.
That's right.
The coherent sheaves are...
Yeah, they don't occur.
Are not the heart of any...
Except in the case of curves. Yeah. Hey, I told you that it would make you upset, so
Oh, I didn't know that.
All right. So now, let's fix that.
What about the Geisiger stability?
You'll see that that's sort of a limit. Again, Geisiger's stability is on this, right? The way you usually define it. We'll see it as a limit. It will occur as a limit, luckily. All right, so now how do you construct these things? We need to do something to make it work, okay? Okay, I don't have too much board space. Can I erase the stuff? Okay. All right, so the following construction is due to Bridgeland, Arcara-Bertram. So Bridgeland for K3 surfaces, Arcara-Bertram in general. And then, there are other things that I've skipped here that, people have contributed. People like Bayer, Macri, Choda. But these are the main people, okay? So the construction is due to Bridgeland originally and Arcara-Bertram for K3 surfaces and Arcara-Bertram for arbitrary surfaces. So now X will be a surface from now. Smooth projectile surface. And I should say, I'm not going to talk about constructions of Bridgeland stability conditions in higher dimensional varieties, but there's a lot of work being done about that. So, but that's a different. All right. So now what do? You have to tilt. Okay? So what you do is you take your category of coherent sheaves. So basically what's going on is like this. You have this coherent sheaves, right? And this function, which is a nice good old function, right? But what it's doing is putting some stuff that it shouldn't be putting in 0. So what you do is you sort of tilt it a tiny bit, yeah? And then try to fix it. And that turned out that it's going to work, okay? So, so tilting, so let's just... So let me make a definition. So a torsion pair. So it will be T and F. So think of this being the torsion, this being free, right? A torsion pair in an abelian category is a pair of full subcategories is a pair of full subcategories of an abelian category, full subcategories of an abelian category A, such that one, again, in order to remember the axioms, you don't have a map from a torsion to free things. So T to F is 0 if T is in T and F is in F, right? And the second thing is that, you can write everything as an extension of a torsion thing together with the free thing, right? So that, and every object, there is a map. There is an exact sequence like this. And for all E in A, there is exact sequence such that T is in T and F is in F. Okay? The usual thing. So a torsion pair is a pair of subcategories. The example that you should think about is, of course, you have torsion sheaves and free sheaves, right? And in the category of coherent sheaves. And then, there are no maps from a torsion sheaf to a free sheaf. And then everything can be written like this. The torsion subsheaf sits inside your sheaf and the quotient is free, torsion free. Okay? All right. Okay. Suppose now you are given an abelian category and a torsion pair. Again, the example here is, example to keep in mind that helps you remember the axioms is that A could be coherent X and T could be torsion sheaves and F could be torsion free. Okay? So that's your example. But, forget about that. So like what you do is that suppose you are given an abelian category plus, let me say it like this. Given the heart of a bounded tree structure, given the heart of a bounded T structure, our abelian category A in the Bridgeland stability and a torsion pair, T and F, yes, oops, I'm making my T backwards. T and F, you get a new heart of a bounded T structure called the tilt. You get a new heart. And it's basically like this. So what you do is that now you look at complexes, right? You are in your derived category, and you require that H naught of this complex to be in T, and H minus 1 of this complex to be in F, right? And then you want every other cohomology to be 0. Okay? I mean, the way you should think about this is that, if you cheat a little bit. Of course, these are complexes and they don't have to have two terms, right? But if you want to simplify your life, just think of these things as two-term complexes where you have a map from an object in F mapping to an object in T. Okay? So basically what we are going to do is that we are going to replace the category of coherent sheaves by two-term complexes. Okay? So we are doing something fairly concrete here. It's not, at the end of the day, it's not that crazy. Okay? All right. So now here is the main constructions for surfaces. So the question is, what will be our torsion pair that we take? So you see, we are again going to, at the end of the day, this is the basic thing we have, the coherent sheaves and the Mumford slope. We don't have all that many things, right? So we need to tilt that. So what you do is you start with coherent sheaves. So maybe what I should say is that you fix a real number. fix a real number, right? And what we are going to do is we are going to say that fix an ample age on x, age ample on x. And what we are going to do is we are going to tilt the category of coherent sheaves with the Mumford slope with respect. So here is what you do. So we have the Mumford slope. So we have, you know, the Mumford slope with respect to h. The Mumford slope induces a Harder-Narasimhan filtration. A Harder-Narasimhan filtration on, let's say, torsion-free sheaves. But, you know, I can extend that to torsion sheaves by declaring that the torsion subsheaf has infinite slope. Okay? Filtration on coherent sheaves where, you know, you declare that torsion sheaves have infinite slopes. So that in this case, like the first part, if you have torsion in the sheaf, the first part is always the torsion subsheaf, and that has infinite slope, and then you get the torsion-free thing, and then you have the usual Harder-Narasimhan filtration. Okay? Okay. And then you see the torsion pair that I want. So it will depend on this S. So you'll define TS to be the following thing. It's the sheaves that are torsion, that have torsion, or have torsion, or the mu min with respect to this Mumford slope is at least SH squared. Okay? And then you have the rest, which is sort of, so to speak, the, so you know, these are torsion-free with mu max less than or equal to SH squared. All right, so then I take, basically what I do, I look at coherent sheaves and I take those where in the Harder-Narasimhan filtration with respect to the Mumford slope, the minimum slope is bigger than SH squared, or the maximum slope is less than or equal to SH squared.
The square is just because you are working on a surface.
Yeah, I'm on the surface. The x is a surface.
Dimensional.
I mean, yes, you can do this first tilt on a higher dimensional variety as well. The problem is that it's still not going to be a Bridgeland stability condition. So to get a Bridgeland stability condition on three-folds, you need to do two tilts.
Yeah.
And then, you know, conjecturally anyway, if you want to get a Bridgeland stability condition on the five-fold, then you would need to do four tilts and things like this. Yeah. But, you know, you'll see that in the proof, you need things like the Bogomolov inequality and the Hodge index theorem. The main obstacle to prove constructing Bridgeland stability conditions in higher dimensional varieties is that you need a Bogomolov inequality not just for coherent sheaves now, but for these kinds of objects and these kinds of slopes.
Okay.
That's what's the hang-up. Okay? All right. So now the claim is that, first of all, this is a torsion pair. Right? I mean, again, this is, you know, fairly clear. If you have any coherent sheaf, right, then, you know, it has a Harder-Narasimhan filtration, and then, you know, you look at the part that's bigger than this, that's, you know, a sub, and then the quotient will be something like this. Yeah, so you can write every object like this, and by properties of slope, you know, you can't have a map from an object like this to an object like that. Okay, so this is really a torsion pair. So then what we do is we do the tilt. Okay, so the tilt of cohex.
Sorry, and any torsion pair can be constructed in that way?
No.
Okay.
I mean, I'm not making any claim like that.
No.
I'm just making that these are torsion pairs.
Those are, but not all of them are.
Not as far as I know. So coex is going to, you know, tilt coex with respect to the torsion pair SFS, right? So what that means is that you get very concretely a subcategory of the derived category, an abelian subcategory that's made of complexes, right? such that if you look at the zeroth cohomology of the complex, right, then the Mumford slope of this one is bigger than SA squared, right, is in TS. The minus first cohomology of this one, in the minus one place, the cohomology is, is an FS, so it's torsion free, and the maximum slope with respect to Mumford is less than or equal to SA squared, and then there is no other cohomology. Okay? And then, of course, you see, I need to also give you a. So far, I described for you a category. But if I want to tell you a Bridgeland stability condition, then I need to give you a group homomorphism from the K group to the complex numbers, right? So, and then what you will do is like this. So it will. So you have Z, H, F, so to speak. Yeah. So here H is our ample, F is any divisor, okay? Oh, am I getting this backwards? Yeah, H is ample, F is any divisor. And you do it like this. You define this thing to be minus the integral over x e to the minus f plus IH, that's the Chern character of E. Okay, and then the claim is that, let's see whether we can keep this a tiny bit. Then the theorem is that this pair is a Bridgeland stability condition. So F is any divisor here. F is any divisor on the surface. H is ample, of course. So the claim is that the theorem, as I said, due to these people, Bridgeland, Archer, Bertram, is that the pair AS and Z FHF is a Bridgeland stability condition. Okay? So let's maybe write this thing a little bit more explicitly. So, if you had RCD for your Chern character of E, say that the Chern character of E looked like you have the rank, you have the first Chern character and the second Chern character, okay? Let's just write down what this happens. If you were to expand this thing, so this looks like 1 minus, so it's minus 1 minus f plus IH plus f plus IH squared over 2 and here you have RCD, right? So you want the degree 2 part of this thing, then it looks like this. Minus D, I think plus F dot C minus, I'm not sure that this is right, F squared minus H squared over 2 dot R. This is the real part, I think. Then it's plus I times H dot C minus H dot F times R. Hopefully that's correct. I mean, we can do it, but so I have F dot H dot R. The I part is like this. I have a minus sign, and then here there is the H and the C, and that one comes with the plus sign. Anyway, I just multiplied it out. So if I integrate this thing over X, right, this is what I get. You take this, the degree 2 part of this product. Yeah? Okay, so now you see the point was that what is it that I want to say? Okay, so now you see we are in good shape. So now like, the problem before was the positivity, right? So let me convince you that by doing this, we got now a positive thing. Okay, so let's check positivity. And then, you know, harder Nursemhand filtration and stuff, you just, those kinds of things are pretty standard. You have, I mean, you know, you have to go to the usual arguments. But so the important thing is that we need to check positivity. And let me sort of argue that and leave it at that. So this is the theorem, instead of claim, that's the theorem of Bridgeland and Archer-Bertram, right? So, so check positivity. So first of all, if you have something of torsion supported at a point, right, at points, then you see this part is 0, this part is 0, but I have minus d here, so that's positive. So I got that it's in the negative reals. So that part, so torsion supported in codimension 2 is okay, right? Because then I have the negative, lands in the negative real axis. Torsion supported in codimension 1, torsion supported in codimension 1, well then h dot c, this is 0, but h dot c is positive, so the imaginary part is positive. So that's okay. Right? So torsion sheaves are okay. So I might as well assume that I have a torsion free sheaf, right? So now let's look at torsion free sheaves. I mean, these things behave well. I mean, they're group homomorphisms. They behave well under exact sequences. So like, you know, you can do it. So if you have a torsion free sheaf, right, such that mu min is bigger than, you know, f dot h, right? So then, but you see, if that's the case, then you see this implies that h dot c, right, right, is bigger than r times h dot f, right? So let's just, you know, right? Because and then you see the imaginary part, then this is positive, yeah? So the key part is that what happens, like the thing that you need to worry about, what happens if mu max is less than or equal to f dot h, right? But if mu max is less than or equal to f dot h, so you see if it's actually less, right, mu max is less than f dot h, then we are again in a good situation, because then you see this h dot c minus h dot fr now this time is less than 0, right? But in this category, I don't have these, but I have their shifts because I put those in the -1. So that changes the sign of this thing. So then but in the category, we don't have our sheaf f, but like we don't have the sheaf. I mean, if you have like mu max of your E is like this, we don't have E, but we have each shifted by 1, right? And that changes the sign so that you get that to be positive. The only tricky part is that what if it's equal? So now you see that's the hard part. The hard part is what happens if mu max, so far I didn't do anything, right? What happens if mu max is equal to f dot h, right? In that case, the imaginary part is equal to 0. Yeah, because then this thing becomes 0. So then what you need to do is you need to check what happens to this thing. Let's do it. So like this looks like minus t plus f dot c minus f squared over 2 plus h squared over 2r, right? So I need to check that this thing is, I need that this thing is positive, right? Because I need to land in the negative real axis, but remember this sheaf is not the one that does this twist, so that changes the sign. So we need to prove that this guy is positive. And I want it to be strictly positive. But you see, this thing is strictly positive. right? So this guy is strictly positive, so it's enough to show that this thing is bigger than or equal to 0. This is what you need to show, yeah? And now here is where you get Bogomolov and Hodge index, yeah? So Bogomolov tells you, Bogomolov inequality tells you that D has to be less than C squared, less than or equal to C squared over 2R, okay? So that this is Bogomolov inequality, so you put it in, so that you get that minus D plus F dot C minus F squared over 2 is greater than or equal to minus C squared over 2R plus F dot C minus F squared. Did I forget an R? Yeah, I forgot an R here, sorry. The R was there. So we have F squared R over 2, right? But now you see the point here is that we want to show that this guy is greater than or equal to 0. But that's Hodge index, right? Because by assumption, we have the C minus RF dot age is equal to 0, right? So Hodge index is telling you that C minus RF square is less than or equal to 0. In other words, the negative of this is greater than or equal to 0. So you see that a lot of math goes into actually doing this little bit of positivity. Okay, and it's worth sort of seeing that you get both the Bogomolov inequality and the Hodge index theorem into it. Again, I mean, the details don't matter too much, but you understand what the difficulty is in constructing this positivity. Okay? And if you want to do this thing now in higher dimension, you need to tilt one more, and then you need to get the Bogomolov inequality for this kind of tilt stability. Okay? That's the difficulty. And you know, whenever you can prove it, then you can construct it, actually. All right. Okay. So this was sort of, at least I wanted you to see an example, and
yeah, I mean, you really want that this inequality is greater than 0.
That's right.
Because the other one, you don't have it. So
Right.
the problem is that
right,
with all the factors.
right.
For higher dimension, there are more.
Yeah, I mean, you know, people have worked out, Bayer, Macri, Choda have worked out exactly what inequalities you need. And, you know, they conjecture that if those inequalities hold, but I think that's hard to prove in general. I mean, you can use other structure of P3 or abelian threefolds and things like this to actually do it in some cases. But I think in general, we don't know how to do this kind of inequality. Like Bogomolov inequality is a difficult thing. It's not such a simple thing.
For abelian varieties, they have.
Yes, those we know. I mean, even for many Calabi-Yaos, we know now.
Yeah, that's true.
Yeah. All right. Okay. So far, this is some abstract thing, right? I mean, I've been babbling for 45 minutes, and you're like, okay, what good is this? So now let's make it good for something. Okay? I'm going to erase all this thing. The only thing that you have to remember from all this discussion is that there is a Bridgeland stability condition on, given a surface, you can make Bridgeland stability conditions.
Yeah,
Okay?
but the main thing is that given a stability condition, you have a moduli space.
Well, we'll get to that. But you see, before I even get to that, you see, the other thing that you need to know is that actually these things are not that crazy. If you want to think a little bit, if you want to cheat a little bit, you can just think of these category as two-term complexes where, you know, the object in the -1 place is, you know, an object of Fs, and the object in the 0 place is an object in Ts. You can cheat. I mean, that's not exactly true, but, you know, if you want to sort of discover a theorem, you first cheat and see what you get, and then you need to worry about the details. Okay. All right. So then here is so now let's see what we can do with this. So you see, we have this complex manifold, step X, yeah. And then I've described for you when X is a surface, like nice pieces of it, yeah. So now what you can do is that to fix a numerical invariant, fix a Chern class, fix a Chern character, say V. right? And now what we want to do is we want to sort of have a chamber decomposition of the stab x. So have a chamber decomposition. And how do you do this? Well, so think of it this way. You know, you have your stability manifold here, whatever this looks like, right? And the point in here looks like A and Z, right? So you have some category and you have some function, right? Well, now what you can do is you can look at the set, and we fixed our Chern character, right? So now what you can do is look at objects in A with Chern character V that are stable, or semi-stable, I should say, with respect to Z. Okay? So, you know, there's some set of objects that are, you know, that are stable, semi-stable with respect to the Z. And they have Chern character V. So now you see, now start wiggling the stability condition, and now you see the objects that are stable with respect to Z and are in this new category are not going to change by much. Okay? So the stable objects will, if you perturb your category a little bit and your function a little bit, then you're not going to change what's stable by much. So think of it this way, right? So you know, I have this new category, right? I have these things, right? If you perturb this S a tiny bit, yeah, and you know, and maybe keep even the function the same, yeah, like it doesn't change that much. The objects that are stable don't change that much. Of course, it can happen that, you know, it can happen that there are some special S where suddenly the things change. Yeah, and that's your chamber decomposition.
Yeah, and sir, using this, did you have aligned in stuff?
That's right.
I mean, this sense, there is just one line, or it's not.
That's right. I'm not describing the entire stability manifold using this.
Yeah, but there is one line.
I'm describing just the S line in there. That's right. Okay. I mean, there's more than one line. There's an upper half plane because you see this is F. Yeah, you know, there are two real parameters. Like say that you have a surface of Picard rank 1.
It depends on age. No?
No, not on age. It depends on this F as well, right? So I have two parameters here. I have the S and the F.
And in some sense, it depends on the age. Because
yes, it also depends on the age. That's right. So there are many parameters here.
So you have a line for...
I have various lines in here. I mean, again, the stability manifold is bigger than that. Again, at the very least, you have this GL2R plus action that sort of acts on it and things like this. But, I mean, it turns out actually that, you know, for some sensible surfaces like P2 and K3 surfaces, you can get most of the interesting stability conditions you can get through that group action from these, basically. At the end of the day, the only ones that I ever want to think about are these. These are the only ones I'll use. I don't want to use, you know, more complicated stability conditions.
But they are.
They're there. Okay. But the point is that you see the objects that are stable with respect to your Z and in this category don't change by much, you know. And then occasionally, of course, they change. And then the theorem is that there is, you know, a wall and chamber structure, where in each wall, where in each chamber, in the interior of the chamber, these like the stable objects, the semi-stable objects staying constant. Okay, I think now it's time to maybe make this thing slightly more concrete. So let's look at P2. So let's actually look at P2. And again, you know, I'm only going to look at these kinds of stability conditions that I described. What happened here? And then you see we can describe the slopes. We can describe what the walls look like. So let's look at P2. But you see, if you have P2, right, I mean, at the end of the day, you know, like this F is also a multiple of H, right? So maybe on P2, let me write it like this. That's not very, I didn't have a very good, you know, on P2, at the end of the day, on P2, you can write everything like this, right? So you can write everything as E minus S plus IT H, where I want T to be 0, S to be any real number times the 2 of E, right? Because P2 has Picard rank 1, so this F and H have to be, so let's call this thing ZST if you want of E. You can write it like this. So now you see, what happens here is that I have some half plane that I'm describing. So I have this, here is the S, here is the T. Yeah, T has to be positive, so we have these Bridgeland stability conditions. Okay. And now the question is, what are the walls? So say that I have a Chern character V, what are the walls? The first thing is that, I mean, it's hard to determine the walls, right? I mean, you want to know exactly when some object of that thing stops being stable and things like this. But the potential walls are easy to describe, yeah? So I mean, suppose that you have a wall, right? So if you have a wall, so on a wall, so you have some object E, right? Above the wall or like, you know, outside that wall, this thing is stable, right? On the wall, it becomes semi-stable. That means that this thing has to have some sub-object F, right? Like this. So, you know, this on the wall, so you need to have a sub-object. And then, you know, this should be destabilizing it. So that means that on the wall, the two slopes have to be the same. Yeah, so on the wall, there has to be a sub-object. There has to be a sub-object such that the slope of F is equal to the slope of E. And then, you know, if you're above the wall, maybe the slope of this thing is less than the slope of that, so it no longer destabilizes. And under the wall, this slope becomes larger and then it becomes unstable. Okay? But now you see, you can work this thing out. I mean, this, you know, we just wrote down the slopes here, right? The slope is, remember, the minus the real part over the imaginary part. And then I can just completely work out what happens. So, you know, say that this has Chern character R prime, C prime, D prime. This has Chern character R, C, D. And then I equate the slopes. You know, I have the mu Z slope, you know, for this object R prime, C prime, D prime is equal to the mu Z slope of R, C, D, yeah? So, you know, I take minus the real part over the imaginary part for one and minus the real part and the imaginary part to the other. And then, you know, you clear denominators, complete squares and something, and you see that they're always semicircles. Maybe I'll skip that part, maybe. Yeah. Or do you want me to do it? I mean, I can do it. It's not that hard. So I mean, what's being said? Let's quickly do it, maybe. I'm not saying anything deep. This you can ask high school students. Even you don't have to. You don't have to go to high school. You don't have to do undergrad. So what you're saying is that minus d plus f dot c, minus f squared minus h squared over 2r divided by hc minus h dot fr is equal to now minus d prime plus f dot c prime minus f squared minus h squared over 2r squared prime, r prime squared, r prime divided by h dot c prime minus h dot f r prime, right? This is what you do. You cross multiply, clear the things, complete the squares, and then you get that this is squared. The cubic terms go away, and then you just get the semicircle, the equation of a circle. Okay? So in other words, I mean, to make it completely precise, I think actually things look a little bit better if you do it again in the slope discriminant coordinates instead of the Chern-Class coordinates. Let's go back to the slope discriminant coordinates. Right? Then I think what you get, the center of the, so you get, so you get a circle with center. You get the circle. Get a circle with center. Mu plus mu prime over 2 minus delta prime over mu minus mu prime. So the picture that you should have is that, let's draw a picture. So it's like this. So here is S equals mu. And then here you have a bunch of semicircles like this, all nested within each other. And this point, the center is minus 2 delta, I think. Minus root 2 delta. I believe. If I haven't, I don't check these things again, okay? But anyway, this is I'm not saying anything deep. This is complete the square and so on and so forth, okay?
And here you're using that P2.
You're not using P2, it's the same on every surface, but then what you need to do is you fix your F and your H. You fix them for once and for all, and you look at the scalings with those, so that you see that picks out for you a half plane, a complex half plane in the stability condition. And the way that that half plane is going to intersect these walls is always like this, in semicircles. And again, that just comes from just equating these things and working it out. Okay? All right.
For any surface, you're getting the same picture.
Well, I mean, the thing that you have to be a little bit careful about is that for any surface on each of these slices, you're getting the same surface. But this thing can be pretty complicated, right? Because as you are moving F and H, right, this thing is moving, you're moving this half plane. And then, these walls are changing. They can start colliding and like crossing, right? But on any slice, it's fairly simple. And you see, this discussion is okay on any dimension. You don't have a Bridgeland stability condition, but you have what's called the first tilt stability. And then, as long as you are dealing with Chern characters that, don't care about stuff or you're asking a question that's not dependent on anything bigger than codimension 2, you can still use this. Like, for instance, on P3, you can bound genera of curves, for instance, using just this kind of stability. Okay. All right. So now let's just all right. Now how to do the next part. Okay, we still have about half an hour. So let's, okay. All right, so this was a lot of abstract things. But at the end of the day, if it weren't useful, then one shouldn't be talking about it. So what kind of problem is this useful for? So here, let me pose the question like this. So here is the question. So what is the ample and effective cone? What is the ample / effective cone of the moduli space of sheaves on the surface? Again, back to what we were talking about yesterday, we have our moduli space, right? And I want to know the ample and effective cone of these moduli spaces, okay? I mean, how do you make a divisor on the moduli space? On the moduli space of sheaves? I mean, how can you get your hands on that? Say that again?
Impose conditions on the objects that it parameterizes.
How? I mean, that's exactly what you do, and then the question is how? Say it again?
The number of sections.
The number of sections, that's exactly right. So you see, the only way, you know, the only sensible way I know how to do this is you look at Brill-Noether divisors or theta divisors and things like that. So let's think a little bit about that. So we want to talk about Brill-Noether divisors. So now what does this mean? So you see what you do is you choose another character, W, right? With the property that the Euler characteristic of V tensor W is 0. Right? So I take an orthogonal character to it. And now you see, take a sheaf. I mean, assuming that there are sheaves, say that you take a sheaf now in this moduli space, right? Suppose that there is such a sheaf. If we have sheaves like this, then you see what you can do is you can define a divisor, or maybe I should call it a virtual divisor. You can define a locus, right, as this set of sheaves in your space. Let's do it like this, such that H1 of F tensor G is not equal to 0. Okay? And the nice thing is that if this thing is not the whole moduli space, then it's some effective divisor. If dg, I mean, I guess I should be a little bit careful. I mean, of course, there's no reason why these moduli spaces should be irreducible. Let's pretend that they're irreducible, like x is p2 or something like that, okay? If dg is not the whole space,
You're using H1 or H2?
I'm using H1.
Because?
Because you see, it could be that, it could be that H0 could jump, or it could be that H2 could jump. But in either case, H1 has to jump. So that I don't have to distinguish between H0 jumping or H2 jumping. I'm being sneaky. But that's a good question. I mean, the question is, why am I not saying that H0 should jump here, right? Which is what you would want to say, right? But you see, on the surface, it could be that, it's not that the H0 jumps, but the H2 jumps. But whether the H0 jumps or the H2 jumps, H1 has to jump. So that this way I don't have to sort of, I'm being sneaky. Okay? Let's pretend that this is irreducible. Assume. Okay? If dg is not the whole moduli space, then you get an effective divisor. Then we get an effective divisor. Divisor on MXHV. Okay?
For any W?
Well, I mean for any G, in fact, right?
No, for any Chern class, I mean, you're fixing the Chern classes, no? I mean,
Well, sure. I mean, for any W and any G in MXHW, you get an effective divisor, right? Okay, but the crux of the matter is that when is this thing, not equal to the whole modular space. So the crux of the matter, when is dg not equal to mxhv, right? And then you see the problem that you face is very similar to the problem that we were discussing yesterday. It's a little bit more complicated version of that thing. It's the interpolation problem, right? Before I was asking, yesterday I asked the question, suppose I have a sheaf in here, what is its cohomology, right? And then you see, you can view that problem as that if you take G to be O, right? Then, you're asking what is the cohomology of O tensor F, and then you're back to the problem we were talking about yesterday. Now I've put a new twist on the problem, is that I'm not just asking what's the cohomology of the general sheaf here, but I'm asking, suppose I give you a sheaf, and then I tensor the general sheaf with that sheaf, and what's the cohomology? So let me call that the interpolation problem. Interpolation problem. So this is given G in MXHW, what is the cohomology? Homology, of F tensor G, where F is a general sheaf. And then you see, you can ask a harder problem, and that you can ask what's the cohomology, like, no matter what F is. You don't have to make.
Here's W and varies V, right?
That's right. Here is W. Here is V.
Right.
And DG will be an effective divisor, assuming that for the general sheaf, this has no cohomology. And in fact, you can go back to the previous problem by taking G to be just O. Okay?
Yeah, but in that case, it's a divisor of DG, with the trivial now.
No, I mean, it would be a divisor if this thing is 0, if the order characteristic is 0. Okay? But I mean, you can also ask this question when this thing is not 0, of course. I mean, this problem makes sense. Irrespective of this condition, it will be a divisor, under this condition, and then the interpolation problem has the puzzle. I mean, if the answer to the interpolation problem is that this has no cohomology, right, then it will be a divisor, but otherwise not. All right, so now.
How big, so how are the changes happen? Does it go from 0 in the general case to 1 in the divisorial case?
Say that again?
Does it go from the cohomology? Do you know how it changes? Does it go from 0 for the general element and then to 1 in the divisorial case?
No, not necessarily. Okay. All right.
I mean, actually you can ask if she's different of 0. I mean, for example, if that mentioned 2 or 3 or 4 or 5.
Right.
Fixed dimension. And you ask for if the dimension is bigger than some number, isn't it?
Yes, you can ask all of these questions. And, then I'm only asking the questions whose answers sometimes I know. If I don't know the answers, then I'm very cleverly not even asking it.
Yeah, but in general, you can ask, not just to be different of 0, to be greater of.
Sure. I mean, you can ask the following question. You can ask, like, describe the locus. I mean, you can ask very generally. I mean, the eventual goal, of course, would be describe the locus, of F and G, so to speak, right? Such that Hi of F tensor G, H1 maybe, of F tensor G is greater than or equal to some number. K, okay. Right. That's right. I mean, eventually that's what you want to do. But, we are very far from something like that for surfaces. So.
Yeah, because they are still that.
Yeah. I mean, even in curves, I think this is very hard still.
Yeah.
So.
We have a lot of answers, but it's not full.
That's right. I mean, I mean, in some sense, even for line bundles on curves, I think this is not a completely understood, right? I mean, there are very famous theorems like the Brill-Noether theorem that sort of answers most of the way these kinds of questions, but you know, it's a hard problem in general. Okay, so now let me explain why I've been babbling about Bridgeland stability. Okay, so now how do you compute cohomology at the end of the day? That's the basics. So when you look at Hartshorne or something like this, you know, he has a whole chapter about it when you about computing cohomology. How do you do it? Yeah, you take various resolutions, right? I mean, you know, the one that he always does at the end is that I think he typically takes the minimal free resolution by line bundles on projector space or something like this, and then hope that from that you can compute it. Yeah? I mean, he never deals with, I think, any question where you need to actually really work hard. Usually the theorems are you multiply with sufficiently large amples so that things vanish and things like this. But here we really need to do it, right? So then the question is, how do you do it? You need to find a good resolution. I mean, how do you find a good resolution? You see, I mean, if you had a vector bundle, right, then the first thing that you should do is you should take its Harder-Nursemhand filtration, right? And then look at its, you know, sort of stable factors or semi-stable factors and hope that you can build the cohomology from that. But of course, you see, this is not very good in this case because we are already starting with a stable bundle, right? So what I want to do is I want to break this thing into simpler pieces, right? And ideally, the way I want to do it is that there has to be some canonical Harder-Nursemhand filtration, right? And then I can look at the pieces and then I can read off the cohomology. Well, and you know, I think Leticia already pointed out yesterday that you can't do that because it's stable. Well, that's where Bridgeland stability comes in. You see, because a bundle can be stable with respect to Giesecker or whatever, but then you have all these Bridgeland stability conditions. And then you can ask, for which Bridgeland stability conditions is this bundle destabilized? And then you see, on something like P2, I just told you that the walls are semicircles. One thing that I didn't tell you, right? This is called the large volume limit. Large volume limit. Okay? What it says is that as you make, so here, remember, this was our s-axis, this is the t-axis. As t tends to infinity, right? Then Bridgeland stability coincides with Giesecker, like the moduli space, the objects are precisely the Giesecker semi-stable objects. So as t tends to infinity, this is, in the physics language, is called the large volume limit, yeah? Then the moduli space, or then the set of semi-stable bundles, semi-stable objects are precisely equal to the Giesecker semi-stable bundles. Right? So then you see what happens is that if you have some semi-stable sheaf, then up here it's Bridgeland stable. Then the game that you want to play is that you want to bring it down until you find the first wall where it gets destabilized. And now you see that gives you a canonical Harder-Nursemhand filtration. And then the hope is that using that, you can compute the cohomology. So that's, I mean, the way I want to use Bridgeland stability is always like that in these talks. Okay? So the idea that you should, maybe let me write this down. The idea is that, you know, it's not possible, it is not possible to decompose a stable bundle in the classical world. But in Bridgeland world, you know, you have a canonical Harder-Nursemhand filtration. You have a Harder-Nursemhand filtration, and you can hope to compute the cohomology using this filtration. I mean, of course, just saying that doesn't help you at all because you need to be able to compute the filtration and, it's not easy, but.
Yeah, the problem would be to descend in some sense.
That's right. The problem will be to figure out when it happens. So let's do maybe some examples. So let's go back to P2. Okay. And let's just start with the Hilbert schema of points, actually. Why not start with the Hilbert schema of points? So Hilbert schema of points on P2. All right, so, so I'll denote this thing by P2n, okay? This is, so this is the rank 1 sheaves. You look at I, Z, and Z is some zero-dimensional scheme, right? So let's start maybe the first interesting cases. Let's look at when n equals 3. Okay, so you have your P2. You have 3 points, yeah? The first question that you ask is, okay, what's the most special divisorial condition do you have on 3 points? That they are collinear, right? That they are collinear. So, so 3 points can be collinear. Collinear, right? And let's put this in this context. Now, what does that mean? What that means is that you see I have a divisor corresponding to O of 1 on the Hilbert scheme, right? So this is precisely the set of Z such that H1 of IZ of 1 is not equal to 0, right? Right? If 3 points are not collinear, then H0 of IZ of 1 and H1 of IZ of 1 are all both 0, right? I mean, first of all, notice that chi of IZ of 1 is 0, right? O of 1 has 3 sections, and then if you impose 3 conditions, then you get no sections and no H1, no H2, right? But if the 3 points are collinear, then H0 of IZ of 1 is one-dimensional, correspondingly H1 of IZ of 1 is also one-dimensional, right? And so you have this divisor that's that's in the Hilbert schema of points, and it's actually extremal in the effective cone. It's extremal in the effective cone. Now, why is that? What that means is that I can find a moving curve in this Hilbert scheme such that it has 0 intersection with this divisor. So, and what is that curve? So if you wanted to give me a curve, like move these points in a curve such that they never lie on a line, how would you do it? So the question is, I claim that this is extremal. And what that boils down to, if you want to prove something like this, it means that you can move these 3 points on a curve such that they never lie on a line. How do you do it?
Maybe.
Let me give you a hint. What happened to the yellow chalk?
Maybe you could
Here.
take like a curve on PG03 and act on 3 non-collinear points.
But that's not, you see, PGL3 is not projective. So you'll run into problems. But here is, let me just cheat. What you can do is you can take a conic. Through 3 points, you can always find a conic, especially if they're not collinear, right? So take a conic, and then, just move your points any way you want on this conic. Right? And the claim is that no 3 of them will ever lie on a line, because, if they did, then that line and the conic would intersect in 3 points, and then that would violate Bezout. Okay? So that's a proof that. All right, let's do one more. So let's do n equals 6. Okay? So now suppose I have 6 points on P2. Okay? So now what do you think is the extremal codimension 1 condition that 6 points can satisfy? That's right. So they lie on a conic, so 6 points can lie on a conic. And of course, in terms of what we've been saying is that then I have dO of 2 if you want, right? Like if I look at Z, right, such that H1 of IZ of 2 is not equal to 0, right? That precisely happens when the conics lie on a conic, and that's the divisor, right? And again, I claim this is extremal. How do you see that this is extremal?
Or you could move 6 points on a irreducible cubic.
That's right. So what you could do is you could take a cubic, right? I mean, to 6 points, you have plenty of cubics. And you see, if you started with, so let me take a cubic. So let's draw a cubic through these points. You see, Joe always says that you first have to draw the curve, then the points. So this was a rookie mistake. So otherwise, you know, you can't pass cubics to stuff like this. So you have a cubic, right? And the fact that these 6 points are not lying on a conic, 1, 2, 3, 4, 5. I lost one of my points when I drew my cubic. So the fact that these 6 points are not lying on the conic means that the linear system of these 6 points on the cubic is not O of 2. Right? So take the linear system spanned by these 6 points on the cubic and, you know, move them within that linear system. They never lie on O of 2. Okay? All right, so, and you know, you can do triangular numbers, hopefully you can do now. So I'm not going to do that. The first maybe more interesting case is that let's look at n equals 12. So suppose I take P2 again, and then I take 12 points. Let me not draw them, there are 12 points. So now tell me what's the, now tell me what the extremal divisorial condition you can have on 12 points.
Like 4. I'm cheating because I already know it, but you have to take the tangents. But still.
Ah, okay, so there's a lot of cheating going on.
They are working on that.
All right, so at least some people are reading the paper. That's a good thing. So, you know, so you see, so now what you have to do is you look at the tangent bundle of P2 twisted by 2. Okay? Now, why am I looking at this? So what's H naught of this? I mean, you see, let's compute. So you see, I have the Euler sequence, right? The Euler sequence tells you that you have a map from 0 goes to O goes to O of 1, 3 copies goes to the tangent bundle, right? Let me twist by 2, so we put the 2 there, a 3 there, and a 2 there, right? And then you see these things don't have any H1 or H2, so if you think a little bit about it, this has 30 sections because O of 3 has 3 sections, 3 of them has 30-dimensional space of sections, this has 6-dimensional space of sections, so you'll get this has 24. So you see that H naught of this thing is 24. Okay? That's good because you see if you have a rank 2 bundle, right, and you ask that a section vanish at a point, that should be 2 conditions, 2 linear conditions. I mean, very generally, if you have if you have a bundle of rank R, right, on the variety, and ask that the section vanish at a point, that should be R linear conditions, right? Because on that set, this is an R-dimensional vector space, and you want it to pass through to the 0 point, so that should be R linear conditions. So that you see, if I have a Z, right, if I have a Z, then you expect, expect that, age naught of IZ tends, this is in, P212. You expect that IZ times TP2 of 2 to be equal to 0, right? Because, I have 12 points, say 12 general points, then I want that, each point imposes 2 conditions, then, it should be that. But you see, now this is actually not so easy to prove, right? Before it was easy to prove because I had a line bundle, right? If I have a section, I want to say that each point decreases the dimension by 1. That's very easy because all you need to do is say that if you can always choose a point that doesn't vanish on any given section, and then the dimension goes down and goes down by 1. Now, of course, you want to choose points so that the dimensions go down by 2, and that's not so easy to do. Right? I mean, this is a hard problem. I mean, whether you can achieve this, right? And if this is really true, then I do get really a divisor. And then again, it's not so hard to see that it's extremal. Okay? So that the thing that we are trying to prove is that deep TP2 of 2, this is Z such that H1 of IZ tensor TP2 of 2 is not equal to 0 is really a divisor. Right? How do we do it? I told you how to do it last time, I think. So how do we get a general set of 12 points? How do you write down a general set of 12 points? So think back to what we did last time at the very end. What were we doing? Okay, you can say it.
So you write the Gaeta resolution.
So you do the Gaeta resolution, right? So I write the Gaeta resolution. Gaeta resolution for 12 points. It looks like this. So you have O of minus 4, 3 copies, O of minus 6, 2 copies. Goes like this. If you have 12 points, the space of cortex, right, is a 15-dimensional vector space. 12 points impose independent conditions. So you have 4 cortex that contain the 12 points. They generate the ideal, and then the only relations on them are degree 2 relations. Okay? It's the Gaeta resolution. Okay, so now you see we can do it. So let's tensor this thing by TP2 of 2, right? So then I get that I have TP2 of minus 4, 2 copies, maps to TP2 of minus 2, 3 copies, maps to IZ tensor TP2 of 2. Right? And now, of course, I win because TP2 of minus 4 and TP2 of minus 2 are both acyclic. So TP2 of minus 4 and TP2 of minus 2 are acyclic. I think this was one of the problems I put down, but it's again easy to see from the Euler sequence, right? So this looks like O of minus 2 goes to O of minus 1, 3 copies goes to TP2 of minus 2, right? So in this case, you see that this has no cohomology, this has no cohomology, so this has no cohomology. And I guess the slightly tricky thing that you have to do is this is Serre dual. These are Serre dual. So you need to check something like that. Okay? Okay. But you needed to do something. This wasn't entirely obvious. I mean, it wasn't hard in this case, but you have to do something. Yeah. So what I want to do, I guess, next time is, if I have a moduli space, so I want to do sort of 2 things next time. So, if I take MP2, the line class V, describe the extremal effective divisor in general. right? So now I can give you any set of points, and I can ask you, okay, tell me what's the extremal divisor. And I can do better than that. I can just look at any moduli space sheaf, any moduli space of sheaves on P2, and ask, describe the extremal divisor. Describe the extremal divisor. I'm going to do this. This is one thing that I'll do. And if I have time at the end, I'll also sort of ask the question of how do you compute the cohomology of the general sheaf on the K3? How do you compute cohomology of general sheaf on K3, the general sheaf in the moduli space in K3. And it turns out that both of these questions, the way basically you solve them is you use Bridgeland stability, and it allows you to find sort of the good resolution. So the game is going to be, how do we find the good resolution? I mean, you'll see. I mean, at the end of the day, somehow here the greater resolution was the good resolution, and somehow I knew that it was the good resolution. But I mean, it happened to be the good resolution, but how do you do it? Okay, and that's what I want to describe. Okay? I think maybe I'll stop there because I already went over time already. So.
Yeah, I don't see how you go from the Geisinger stability to Bridgeland stabilities. The limit, okay, I agree that the limit is going to be the Geisinger stability, but then how do you get that line that you draw?
Oh, how do you go down?
Yeah, how do you...
Well, I mean,
First of all, how do you prove that Geisinger stability is Bridgeland stability?
It's not. I mean, what I'm saying is that, like, if you make T sufficiently large, then I'm saying that the only Bridgeland stable objects are going to be Geisinger semi-stable. Okay. But, that comes just from the formula. I mean, I erased that. You write the formula, and, basically what has to happen is that, if this thing is stable past a certain point, right, then none of the sub-objects that you have are going to, like you get, like in the limit as T tends to infinity, you recover the Geisinger slope.
Yeah,
from that formula. I mean, you have to play with the formula.
That line is defining some S.
I mean, you have some category AS, right?
Yeah.
So what's happening is that you have this category AS, right? And you can fix your S if you want. So the category, if you want, is not changing. Right? The category depends on S. The function depends on both S and T. So basically what you're doing is that you're putting some T's in this formula, right? And as you change T's, the slope that you're computing is changing. Right? So what's happening is that you have this category AS, right? And then the question that you ask are, what are the semi-stable objects with this category AS with respect to this function, ZST? And then the statement is that if T is sufficiently large, the only stable objects are Geisinger stable sheaves. So that basically, if you think about the moduli space or the moduli set even,
I mean, you say that Bridgeland stability are contained in the Geisingers, but they are not exactly the same.
Well, I mean, it depends on what you mean the same. So like you see, what I'm saying is that you fixed your Chern character, right?
Yeah.
So you have this category AS, right, that are so in this category AS, you have objects with Chern character V, whatever they are, right? And then you want them to be stable with respect to this Bridgeland stability ZST. But this function is changing, right?
Yeah,
I mean, the function is changing.
Yeah, but when you take it T very large...
So what I'm saying is that if T is very large and you have an object that's of this category that's stable with respect to ZST and of Chern character V, then it has to be a Geisinger semi-stable bond sheaf.
Not a Geisinger stability is Bridgeland stability without T very big.
No, I mean it's an if and
With
the geese. No, it's an if and only if. Giesecke semi-stable things are Bridgeland stable if T is really large, and those are the only ones.
Yeah.
It is an if and only if statement. But you know, like
But
we are comparing objects that are stable. I'm not comparing stability conditions or
No,
anything.
that's
Okay, so that's the distinction. Yeah.
yeah, but I mean,
So the
general basic stability is stable is
right, then the moduli, if you want to, like, the moduli space is isomorphic to the moduli space of Giesecke semi-stable objects. So let me say it like that. So that makes it, that's the point. Okay. I mean, I didn't talk about the moduli spaces for these Bridgeland stable objects, so that's why I'm not.
Yeah, that's another question.
Yeah, I
You
mean,
construct the moduli for
that's right.
You construct the moduli spaces for these stability conditions using GIT or
No, you
it's
can't.
different?
Well, I mean, yes and no. So you see, you don't use GIT. I mean, you construct it first as a stack. Then you need to exhibit an ample bundle on them. And then you see, the problem is that we don't know that such things exist. We know it for certain types of surfaces that these are projective. It happened that for P2, we originally proved this thing with GIT, like with Aaron and Jack and Daniele. Originally, we proved it using GIT, but we proved is that on P2, every Bridgeland moduli space is isomorphic to a quiver moduli space. And then you can use the GIT on the quivers. But that's very special to P2. I mean, you know, a random surface is not going to have that kind of structure.
Okay.
Are there any more questions? Can you say something a little bit about these Brill-Noether loci? That once you have a divisor, but then is there? I mean, can you make some comments on? Say back to the stuff you mentioned yesterday, that the general element has no homology, or at least one group which is not zero.
Right.
Outside that loci.
Like, what does that locus looks like? Well, you see, it really depends on what you are asking.
I'm sure there are a lot of exceptions.
I mean, okay. So you could always do the following thing. You see, no matter what my okay. Okay. So if you are thinking about the Hilbert scheme, you see, you can ask for the ample cone of P2n. Okay? And this you can completely describe, for instance, yeah? So, what?
I think for this case was in problem set.
Okay, so let me tell you what the answer is. So you see, the other kind of question that I can ask, so I've been asking what's the most special kind of divisor that these points can satisfy, right? What's the visorial condition that these points can satisfy? I can ask what's the most special kind of curve these points can be on, right? So yeah. Again, that's easy to describe, and it's much easier to describe, actually. You see, the most special kind of curve that a bunch of points can lie on is that, you know, you put them all on a line and slide one point. Right? In other words, the most special position in which these points can lie on is if they're collinear. Okay? So, said another way. So I think, let me put it like this. You see, how do you get divisors? Like, you know, on the Hilbert scheme, you have the following thing. So fix a line. This works on any surface. So say you have X and fix a line bundle L, right? Then I have a map X to the N a rational map to the Grassmannian of, you know, H naught of L and H naught, maybe H naught of L minus n-dimensional subspaces, right? So, and what you do, you send a point Z to H naught of IZ tensor L, right? And I mean, this needs to make sense. So n had better be less than or equal to H naught of L. Okay, so I need n less than or equal to H naught of L. Otherwise, it's not such an interesting thing. Maybe let's in fact stay strictly less than. Okay, so you have a rational map. So given Z, you can ask, you know, right? And then you have a divisor. Again, you can view this thing as a Brill-Noether divisor if you want. I mean, you know, a given section of this thing will be when this thing, when the, you know, okay. All right. And then you see the question is now if you're on something like P2, like if I have P2n, right? Then I claim that the map to the Grassmannian of, so here is O n minus 1, OP2 of n minus 1, mapping to, so whatever this is, n plus 1 choose 2 minus n. I claim that this is a morphism. This is a morphism. It's not just a rational map. But it's not an embedding, but it contracts. Precisely this kind of curve, okay? Like it contracts the locus of lines that are. So, you know, I mean, there are cases where you can describe exactly what I mean, you know, now if I take like Brill-Noether divisor a little bit less ample than this, right, then the base locus is precisely going to be that. Right. I mean, so, you know, there are cases where you can describe this, but in general, you know, it's a fairly complicated thing. I mean, I don't think that you will ever be able to describe the following thing. Like, you will ever be able to describe the Brill-Noether loci of, on a surface, the Brill-Noether loci that come up. I mean, even on P2, you're never going to be able to describe that. I mean, it's just way too complicated, right? I mean, you will never be able to describe the collection of points that fail to impose independent conditions in a line bundle on P2. I mean, there's no other description of that locus. That's what it does.
Right.
Right? I mean, you know, when it's lines and conics, there's some extra geometry that you can just say what happens, right? You know, for instance, if you want to know when 4 points fail to impose independent conditions in conics, that happens if and only if they're collinear. But, you know, that kind of thing is just very special. It doesn't happen. I mean, if you're talking about degree 17 curves and like 100 and whatever many points, that's just what it does. They are not going to satisfy any special smaller degree equations, I don't think. So describe it. Yeah. I mean, yes, I can describe it as the set of points that fail to impose independent conditions, but I don't think that there's an independent description of those loci.
I don't know. I don't agree.
You don't agree?
I don't. I'm not familiar with this thing of counting curves or points or anything like that. But, for example, I mean, for the Brill-Noether loci and some curves, one way that we construct the Brill-Noether loci was taking extensions.
Yeah.
For example, if you do have a vector bundle and then the trivial bundle as a sub.
Right.
So the problem was to prove the stability.
Right.
But then you have a bundle that has sections.
Right.
I think that similar things can be done actually in any variety. You know? Do you construct bundles with certain number of sections in different ways? One is using extensions, the other using elementary transformations. There are some methods that have been working for curves, and I think that some of them can work on some.
I mean, I agree that you can find points that way, but I don't think that the general such thing is necessarily given that way.
I agree with that. But
So like what I'm saying is that, so, you know, what he wants to describe is, for instance, you know, say that you have some large number of points and that are failing to impose independent conditions on the So you know, for instance, one way you can do this, you can put all the points on the line, and it will fail to impose independent conditions. But that's not the general point. And I don't think that the general point will have any other description than that it just fails to impose independent conditions. I mean, it just there isn't.
Yeah.
I mean, you know, whenever there is, it's a famous theorem. I think you call it the Cayley-Bahara theorem or something. So you know, I mean, in general, I think it's just what it is. That's the description of the locus. I mean, you know, there are still questions you can ask. What's the dimension? What happens? How many components?
When is non-empty?
Right, that one you can describe the way you can do it. The way you're describing, you'll be able to say when is it non-empty. But you know, I already am telling you that, like, you know, this locus, like, you know, once you put all the points on the line, then that will be in the base locus of anything that's less ample than this guy.
That's right.
So, you know, they will be non-empty, but, you know, I mean, the dimension will grow at certain steps.
The dimensions, for instance.
That's right.
And what lies in the closure of what?
I mean, there are cases when you can do it. I mean, you know, it's just... But again, I mean, you know, the basic theorem, again, in this case is that if you have 2n plus 1 points, right, then they impose independent conditions on curve with degree n and p2, as long as no n plus 2 lie on a line. I mean, you know, in that region, then you can describe this thing because they lie on a line or something like this. But you know, that's a very special theorem.
Yeah. Besides, it covers just a fraction of what's happening.
That's right. Yeah. No, I mean, I don't know the dimensions or the how many irreducible components and what can happen. So.
But it would be a determinantal variety?
Yes, they are determinantal.
You can expect some dimension.
You can expect some dimension. It's not always true. I mean, you can easily give examples where it's false, but sure, you have an expected dimension, but it fails typically.
For the general doses.
Yeah. No, I mean, I think that we are somehow not quite at that level, at that place where you can describe these higher things yet.
Right. Okay. All right.
Maybe that's a good question. I don't know how to do it.
All right. Well, if there are no more questions, do that. Let's thank.
Probably, I mean, if you have time, we can discuss with Hugo and Jornadas because they are working on Brill-Noether.
Okay.